One of the most wonderful things about the universe is that it's incredibly imaginative, far more imaginative than we are. When we look up at the night sky, we just see these little pinpricks of light. But if you really understand what you're looking at, if you let the physics tell you the story, those pinpricks become real places. Today, let's do a little thought experiment. Let's imagine we figure out a way to travel 600 light years, which is a whole other problem with relativity and energy that we won't get into right now, and we actually arrive at a star in the constellation of Cygnus. We're going to a planet called Kepler-22b. What would it actually be like to stand there? What would you see? What would you feel? Let's figure it out together.
The very first thing you have to understand about Kepler-22b is that it is big. We call it a super-Earth, which is frankly a bit of a misleading name because it tricks your brain into thinking it's just like here but with more real estate. But nature doesn't work like that. When you change the scale of something, you change the physics of how it operates. Kepler-22b has a radius about 2.4 times that of Earth. Now, think about the geometry for a second. If you double the radius of a sphere, the volume goes up by a factor of 8. This thing has over 13 times the volume of our planet. So, what happens when you step out of your ship space? Well, you immediately run into a profound mechanical problem: gravity.
Gravity depends on mass. If this planet is made of rock and iron like the Earth, the mass would be enormous and the gravity would be absolutely crushing. Let's say you weigh 150 pounds right now. On a rocky Kepler-22b, you might suddenly weigh over 350 pounds. Try to imagine that. Your muscles, your bones, they evolved to hold up 150 pounds. Suddenly, every time you lift your arm, it feels like you're lifting a bowling ball. Your heart, which is just a mechanical pump really, has to work more than twice as hard just to push the blood up your neck against that gravity so you don't pass out. You wouldn't be doing any exploring. You'd be lying flat on your back, exhausted, just trying to breathe.
But here is where the puzzle gets really interesting, and where the super-Earth name completely falls apart. If you look at how planets form out of the swirling disks of gas and dust around young stars, a planet this big usually doesn't stay just rock. It has so much gravity that it grabs onto lighter stuff, hydrogen, helium, and massive, massive amounts of water, and it holds onto it. It doesn't let it boil away into space. So it is highly likely that there is no ground to stand on at all. Kepler-22b is probably a water world. Imagine an ocean, but don't imagine the Pacific Ocean. The Pacific is just a thin little puddle on the surface of a rock. I want you to imagine an ocean that is hundreds, maybe thousands of miles deep, wrapping entirely around the planet. No continents, no islands, just a sphere of liquid. Now, let's put you in a boat floating on this ocean. What's the weather like? Well, Kepler-22b orbits a star that is very much like our own Sun, a G-type star, and it orbits at a distance where the amount of light and heat it receives is just right. It's what we call the habitable zone. Not so hot that the water boils, not so cold that it freezes solid. If it has an atmosphere like Earth's, the average surface temperature would be around 72 degrees Fahrenheit. It's room temperature. It's a beautiful spring day. So you're in your boat. It's 72 degrees. You look up. The sun and the sky would look incredibly familiar. It would be a bright, yellowish-white disk, maybe just a tiny fraction dimmer than what we are used to. It would move across the sky a little faster than ours does because the planet is closer to its star and moving faster to stay in orbit. A whole year there only takes 290 days. But the sky itself probably wouldn't be a nice, clear blue. Remember that enormous gravity? That gravity holds on to a very thick atmosphere. A thick atmosphere over a global warm ocean means you are going to have incredible amounts of evaporation. The air would be extraordinarily humid, heavy and thick with clouds. It would likely be a very hazy, overcast world. The light from that familiar sun would be scattered and diffused, casting a strange, even glow over the rolling waves. And those waves, Without any continents to get in the way and break up the weather patterns, the winds could whip across that global ocean for thousands of miles, building up swells that would make the biggest waves on Earth look like ripples in a bathtub. You'd be riding these immense, slow, dark mountains of water.
Now, just because we are scientists, we can't just stay on the surface. We have to ask, what's underneath? What happens if you take a submarine down into that global ocean? This is where the physics gets truly wild. As you go down, the weight of the water above you pushes down. Pressure builds. On Earth, at the bottom of the Marianas Trench, the pressure is about 1,000 times what it is at the surface. On Kepler-22b, because the ocean is hundreds of miles deep and the gravity is stronger, the pressure at the bottom becomes incomprehensible. It gets so high that it literally forces the water molecules to lock together into a solid lattice. It becomes ice. But it's not ice like you put in your lemonade. It's a special phase of water we call ice II, or ice X. Because it's so deep down, it's actually incredibly hot from the planet's internal heat, hundreds or thousands of degrees, but it is crushed into a solid state by the pressure. You have a shell of burning hot ice wrapping around the rocky core of the planet. The joy of the puzzle. You see, this is what is so beautiful about physics and astronomy. We didn't send a probe there. We didn't take a picture of this ocean. All we did was watch a star. We watched a star 600 light-years away get slightly dimmer for a few hours every 290 days as a planet crossed in front of it. From that tiny little shadow, we figured out the planet's size. From the star's light, we figured out the temperature, and from our understanding of atoms, gravity, and thermodynamics, we can construct this entire alien reality. We can sit right here on Earth and know that out there in the dark, there is likely a warm, hazy, endless ocean rolling under a familiar sun, hiding a core of burning ice. Nature provides the rules, and if we are clever enough to read them, we can explore the universe using nothing but our minds.